Hey guys, as I promised, here's your video from the PowerPoint where I left off. We'll start at the slide that says types of synapses. Okay, two types that are very traditionally found, that they're very common. That's the axodendritic and the axosomatic, and then there's three that are not. The axodendritic, well, the name really dictates how the neurons are placed together. Axodendritic means axon to dendrite. So the axon is facing and close to the dendrite. The second one is axosomatic. Okay, that's going to be the axon of one neuron facing the cell body of another neuron. The less common, there's going to be the axonic, that's axon to axon. The dendrodendritic, that's dendrite to dendrite. And the dendrosomatic, that's going to be dendrite to cell body. Keep in mind, between each neuron is going to be a synapse, a space. Okay? The next one is chemical synapses. Those are specialized to allow the release and reception of chemical neurotransmitters. So these synapses have a chemical makeup to allow this to occur. The typical chemical synapse is made up of two parts: an axon terminal of a presynaptic neuron, which contains many tiny sacs that are full of neurotransmitters. And then second, the receptor region for the neurotransmitters is going to be postsynaptic. It just so happens I always have something to draw with because I am the queen of drawing. Hey, okay, so let me draw real quick. Okay, rudimentary, I guess. If you can see the one that looks like it's long and it's got three lines on it, that's the axon and the terminal endings, and the dots on it, well, those terminal endings have the sacs that are going to have the neurotransmitter in it. The space between the two is going to be the synapse, and then on the other side, the one with the circle is the cell body, and those are dendrites that are specifically allowing the neurotransmitter that can bind there. Once that occurs, chemical reaction. Okay? Hope you like that drawing. Not just in class, I'm going to get you here, huh? So that's the chemical synapses. Okay, and what it compares of? The synaptic cleft, okay, these synapses, they cannot be dry. They have to have fluid within them. Because let's think, what do they tell you when you're having a lightning storm? They tell you not to go in the pool. Why? Because pool can conduct electricity. Same idea is within this. So within that synaptic cleft, that space that is going to be between two neurons is going to be fluid filled to ensure that information or an impulse from one neuron that's before it, presynaptic cleft, goes through the synapse to the postsynaptic cleft. Does that make sense? I hope so, because that should. So again, it's fluid filled to allow this to transfer through. The current must go from one to the other. These are going to help movement of an impulse. Chemical synapses prevent a nerve impulse from being directly transmitted from one neuron to another. So in a synaptic cleft, normally speaking, the fluid in it passes from one neuron to the other. But if there is a chemical synapse there, it will prevent it from moving further on. It'll stop after that one neuron. Okay? The impulse to be transmitted is going to depend on the release. the diffusion, the receptor binding of the neurotransmitter molecules. It depends on a few things. Okay? Let's see. What else? It doesn't look good. Okay. Information transfer. There's obviously going to be a chain of events that occur for neuromuscular junction, which is a great example of chemical synapse does. Try that again. There has to be 6 ways that a chemical synapse functions that you can learn. And in fact, there are 6 ways. Okay? All right. First, the beginning of a chemical synapse is when the action potential arrives at an axon terminal, meaning the action potential has now come from the dendrites, the cell body, to the axon, to the end of the axon, which is the terminal portion of it. Okay? That's the beginning of this chemical synapse. Second, what I said in number 1 causes calcium channels to open. Voltage-gated channels of calcium also open. This causes a change in the electrochemical gradient. This change, or charge change, comes from the extracellular fluid into the terminal. Think. I want you to draw this as I'm saying it from 1 to 6. So sheet of paper out. Draw out the one thing, the first step. Now draw out. At the end of the first step, you're now having calcium channels opening, causing calcium to come in. What does that do? It changes the charge of the neuron. Okay? Number 3. All this calcium that is now in the axon terminal acts like an intracellular messenger. What does that mean? It means that it causes something chemical to happen. This thing that's chemical is going to be synaptogen, that's the best way to spell it, which is a protein, binds with calcium. When synaptogen binds with calcium, it's going to interact with other proteins in that axon terminal. Remember, our neurotransmitters always cause a cascade of events. So we got synaptogen bound with protein and calcium. Then we see that molecule that's made, that synaptogen molecule, now interacts with other proteins. Now, because of all that, the synaptic vesicles fuse with the axon membrane. This all causes the contents to be emptied in the synaptic cleft by exocytosis. Again, may I help? I'm trying to get it in. Okay, neuron, okay? So what's going to happen is, step 1, it's going to travel all the way down to the terminal endings. Step 2, because it's traveled all the way down to the terminal endings, calcium's going to rush in. When it rushes in, it's going to bind with synaptogen and make this huge molecule. When that occurs, it's going to start not talking with, or communicating with, binding with other proteins that are in there. Name's not important. When it starts doing that, it causes this macromolecule to bind to, okay, the membrane, which causes contents to empty into the SC, or synaptic cleft. So far that's where we're at, okay? This camera's hard for me to communicate with. Sorry, I'm doing the best. When it empties its contents by exocytosis into the synaptic cleft, step 4, neurotransmitters that were released by that exocytosis diffuse across that synaptic cleft to bind with receptors on postsynaptic membrane. It should sound like the muscles. Remember we talked about muscles, okay? Same idea. So now it's released into the synaptic cleft by exocytosis. It can travel through the synaptic cleft because it's fluid filled, and then on the other side here comes a new neuron for it to bind with. Okay, that's what happens. Number 5, the binding will open ion channels, causes something to occur. Neurotransmitter always causes something to happen. Opens ion channels, depending on what type of neurotransmitter it is, causes the neuron to be either excited or inhibited. So the neurotransmitter goes across, it binds. It depends on what neurotransmitter we're dealing with. It's either going to excite that postsynaptic neuron or inhibit the postsynaptic neuron. It depends on which one it is. Number 6, it's done its job. So now that neurotransmitter has to be terminated. And it is. Not so bad. Draw the pictures, it'll help. Again, the slide underneath the information transfer, you have an image of what I've said. It looks very much like what we talked about in, there it is. It looks very much like the muscle one. Go through it, draw it, and write in your own steps. It will help you memorize this. Okay? Next one is termination of the neurotransmitter effect. The binding of the neurotransmitter to receptors is reversible, means it can be taken away and changed. As long as it's bound to the neurotransmitter, continues to have its effects. And it also blocks any additional signals from occurring. Meaning, you've got something it's going to bind to, okay? If it comes in and binds to it, it's blocking any other neurotransmitter from, I'm trying to get this, it's blocking any other neurotransmitter from getting in. The effects are still going on, but nothing else can come in and have effect on it. The minute that this comes off, this receptor's open for another one to come in. Okay? There's 3 ways to degrade. Degrade means get rid of the neurotransmitter from being in that binding site. You're going to degrade the enzyme. So an enzyme lands on top of it while it's bound and breaks it apart. The other way is reuptake by astrocytes or axon terminal. Astrocytes get involved and take it away from where it's at. Diffusion away from the synaptic cleft. Somehow it breaks away from its binding site and it diffuses away from the synaptic cleft from those receptors that it was there with. If it does any of those, then it's done. Okay. Postsynaptic potentials. There are many receptors on the postsynaptic membrane at chemical synapses. They're specialized to open ion channels. Unlike the voltage-gated ion channel responsible for action potentials, these chemically gated channels are relatively insensitive to changes in the membrane potential. Meaning if the membrane potential, the charge of the membrane, alters, it doesn't really have an effect on these ion channels. Okay? Because of this, channel opening at postsynaptic membranes can't possibly become self-amplifying or self-generating. At postsynaptic, take apart what I'm saying to understand it. Postsynaptic membranes, okay, that's the membrane after the synaptic cleft, okay, they can't possibly be self-amplifying. They can't make the impulse stronger, and they can't make the impulse themselves. They cannot be self-generating. It has to come from somewhere. Okay? These neurotransmitter receptors have a moderately graded potentials, meaning it varies in strength. It's going to vary in strength according to the amount of neurotransmitter released and the time it remains in the area. That's, anything else. A lot of medicine knocks you out. A little medicine, you don't feel a thing. Same idea. The time it remains in the area, if I tell you to hold something in your mouth and to make it numb, the longer you hold it in there, the more numb your mouth is going to feel. Okay? epsps, okay, that's excitatory synapses. At an excitatory synapse, neurotransmitters binding depolarizes the postsynaptic membrane. Remember, what's the definition of depolarization? That's where it spikes up and gives the strong impulse. Postsynaptic membrane, what's that? That's the one again after the synapse. Right? Chemically gated ion channels open on postsynaptic membrane. Each channel allows sodium and potassium to open simultaneously to diffuse in opposite direction to maintain a charge. Wanting depolarization, you think even with both diffusing, but it is not, because sodium gradient is much higher than potassium. They're both diffusing simultaneously. You think, oh boy, it's got to be because they're diffusing simultaneously that it's occurring. No. Potassium's not as strong as sodium as far as changing a gradient. Okay, so it's different. If enough neurotransmitter binds, depolarization of postsynaptic membrane can reach axon's threshold for an action potential. Okay? Pretty self-explanatory. Explains how it kind of works. Keep in mind, excitatory is to build up. Okay? Synapses. Look at the name for understanding what these things mean, because if not, I'm reading words to you and you have no clue what's going on. Think about the words that I'm saying to help you understand. Binding, the next one, inhibitory synapse or ipsps, inhibitory. That means it inhibits the function of. Okay? Synapses inhibits the function of synapses. Kind of goes together. The binding of neurotransmitter at inhibitory synapse goes down a postsynaptic neuron ability to generate an action potential. You've deduced that yourself by listening to the terms that I just said. The actual definition of it makes sense. Okay? So the inability to make an action potential. Most inhibitory neurotransmitters hyperpolarize the postsynaptic membrane by making the membrane more permeable to potassium. You know hyperpolarization has to do with potassium channels staying open longer than they should to allow back in resting state. Okay? All right. All right, the good news is the chemical classes of neurotransmitters, I'm not asking you to break down and define each one. You just have to know the 6 different classes. So if you get a question like, which one of the following is not a chemical class of a neurotransmitter? There you go. You know the different classes. Okay, so make sure you go through that. It's listed for you on the slide, should help you out. Neurotransmitter receptors, there's 2 that you have to worry about. Okay, they're either going to be a channel linked receptor, which mediates fast synaptic transmission, or a G protein linked receptor, which mediates slow synaptic receptors. If you look at the pictures that's on the slide, you can get why. A channel linked means the neurotransmitter hits a receptor, goes through, causes a chemical reaction. Pretty fast. Okay? G protein linked receptors, okay, neurotransmitter hits G protein has to attach to this, has to attach to this, has to make this, has to drop off this. You can see it in the picture. It's going to take a lot more time. Makes sense. If you look at it, you understand. The next slide is organization of neurons. Okay, neural pools. Okay, neural pools is the definition is neurons in the central nervous system organized into these functional groups. Neural pools are nothing more than central nervous system functional groups. Okay, circuits. Circuits are pattern of synaptic contacts within a neural pool. A pattern represents a different function. You know what a circuit is? You've seen it in a computer. They're green and they have metal things stuck into them. Okay? They all look different, which means they all have a different function. Your circuits look like that. Well, not necessarily green with metal in it. But your circuits were all wired differently because we look differently, we act differently. Same idea with a circuit. Serial processing. This works in an all or nothing manner. It starts and it has to get to the end the way it started. A bad example of it would be that telephone game, you know, where you start at one person, you tell them a secret, and by the time it passes it all the way around the room, it's completely different and it makes no sense. That failed the all or nothing exam. Reflexes, I talk about all the time. It's a rapid automatic response to stimuli. A spider on you, no matter how many people like spiders, you're going to swack at it, smack it, freak out, scream, jump, whatever. Those are reflexes. Okay? Parallel processing, kind of like the name suggests, inputs are segregated into many pathways, but they're dealt with at the same time. That's kind of like things are coming in, that's a guarantee that it's going to be dealt with because it's going down different pathways to get there. So one of these ways is going to work. Okay? It's kind of fun talking. Maybe I'll miss next class. No, I'm just kidding. Okay? Now it's just disabilities. Let's start with my first one. It's not on there. It's multiple sclerosis. Multiple sclerosis is an autoimmune disorder. It is where the cells of the person that has multiple sclerosis attack their myelin sheaths. Meaning, so we talked about how myelin sheaths are made by Schwann cells or oligodendrite cells on the axons. Well, these cells see the myelin sheath as the enemy, as like a bacteria almost. And then what they do is they cause lesions. These lesions really are just patches of inflammation. The loss of these myelin sheaths kind of depletes the idea of impulse conduction. Okay? It kind of starts off, I mean, it can be eyes not functioning well, muscle spasms, pain in the muscles, fatigue, emotion. You start with minor things that just don't work well. You stop walking very well, you stop being able to lift things and not have physical strength, to the point you can't swallow, you can't eat, you can't take care of yourself to go to the bathroom, and you're bedridden. You want to say something to your spouse, but you can't even look at him and say the words. So MS is really a pretty debilitating disease. It affects your family and them very physically and emotionally. It's sad to watch. The next thing is Bell's palsy. Wicked cool disorder. I put it on there because I thought it was cool. Is a nerve controlling movement of the muscles of the face. It happens in the 7th cranial nerve. And what happened is it paralyzes. All of a sudden. It could be an inflammation near the nerve. It could be herpes, it could be Lyme disease causing it to function. It could be a severe middle ear infection. All of these things can cause it. We can't really narrow it down to too many things. But if you look at the pictures, you'll see it looks like one side of the face looks like they're winking at you, but it's a whole side of the face. And in this, all of a sudden you're better. You get improvement. It's over time, all of a sudden it comes down and it looks normal again. I guess it depends basically on how long it takes for the inflammation to go away by that 7th cranial nerve. But it goes down. The last one is dedicated to someone I definitely love dearly. Her dad passed away. He had Alzheimer's disease. And Alzheimer's disease is a loss of brain function. It causes various stages of dementia. It gets severely worse over time. There's really not a 100% thing that I can say is the cause of Alzheimer's disease. There's a lot of speculation on what they think what causes it. It does show changes in the brain. If you look at the image, the left is normal and the right is somebody with Alzheimer's. You can see the whole brain looks normal. The right side for Alzheimer's brain, it looks like it's kind of sucked in. You can see the bottom, the Alzheimer's cutaway. There's more black. You can't really depict the difference between white and gray matter because you're losing so much of it. There's no cure for it. And it's really sad. And the risk factors, believe it or not, female. Anyone with heart or blood vessel problems, cholesterol, anyone that's had a head, trauma, but that's not guaranteed. You could still have it and not have had any of these effects. There's not much we can do except for try to support the family and make sure the person with Alzheimer's doesn't get hurt. But as my friend would tell you, there's good days and there's bad days, and the bad days are really, really bad. So I hope and pray to God you don't deal with any of these disorders. But I hope this helps a lot, and it helps you study. Study, study, study. I want A's. All right. Goodbye.